Okay, so how do I do this to make it? Okay, wait a minute. Zoom. Fast. That's not zooming at all. Oh, there it is. Wait. Okay. Why is it not working? You know, I could probably use a single aspect ratio. Let's see. Okay, so if I did that, here's what I'll do. I use the the erasers. So this is where one edge is. And let's see, right there. That's not bad. So if I come in today and just draw a line here, line here, that's almost, yeah, it's still not a 16 by 9, but there's a part of the board, let's see, yeah, that'd be fine. All right, everything is an adjustment. So I'm going to sit here for a minute and then we'll start. Actually, maybe next week I'll start looking at the actual problems. But wait, Labor Day's not this coming Monday, is it? Or is it the next?
No, it is. So there's a Monday, and then it's Labor Day.
Labor Day's on Tuesday?
No. It's one Monday a week, and then the next coming. 2 Mondays from now is what I'm trying to say.
Okay. So it's actually, okay, this coming Monday is the 29th.
Yeah.
So it's the 5th.
It's after that.
Okay, so it's the 5th. Okay. So we'll have a full next week and then a shortened week after that. Okay. All right, so my feet are killing me, but we're going to just start and go through this. So let's do, and we'll come back and work problems in chapter 1. But I think since next week is, we'll have Monday as well, I'm going to come back and work some problems on Monday in chapter 1. The fluid statics is kind of not weird, but they kind of describe it like the guy I took fluids from first. He had this thing where he had an oak barrel. How can you bust an oak barrel with a glass of water? And the key is you actually can do it if you put a very, very thin tube and you fill it up to here, because the pressure, so if this amount of volume that's in this thing, this small volume, say glass of water, you can fill this barrel up to the point where there's so much pressure in there, it'll pop the seams. He was talking about an oak barrel. He had a video. An oak barrel with those straps on it, like a wine.
Oh, yeah, I got you.
And you can get those up in Altus and stuff. So the question is why? And it turns out it's not that surprising. Let's say you took a perfectly cylindrical glass. Doesn't have to be glass, it can be metal, but if it's glass, you can see through it. Then you set it on a scale. And on that scale, of course, I don't know how to do this, so here's a meter that measures the weight. Now, we knew from chapter 1 that there was density, which is the mass per unit volume, but there was also the gamma, which is the specific. So this is density. Here, I'll write it this way. So this is still from chapter 1, I guess. This is specific weight, and it's the weight per unit volume. Turns out for water, it's around 62.4 pounds per every cubic foot of volume you've got. So you have the weight given a particular volume. Now let's assume that this has an area up here. Now you know the area is going to be pi r squared, but I don't even care about that. All I care about is that the area doesn't change as I go up and down this. It doesn't matter what slice I'm taking. The area is just a constant. And so I fill this up to a certain height. And say I fill it to the top, although I don't have to fill it to the top. But before I put the water in there, I zeroed the scale out. So I zeroed out, it had 0 weight. Then I filled it to the top. So what's the weight of the liquid in there? So the weight of the liquid is going to be the area. I didn't put the height in there yet. So it's a certain area that remains the same as I go up and down the glass, although it doesn't have to be glass. It actually doesn't even have to be circular. It can be a metal box. As long as the area doesn't change as you go up and down. So if the area doesn't change as you go up and down here and take slices, then this all applies. So it could be metal, it could be anything, as long as it's a constant area up and down. You have it on a scale, you zero it out, whether it's metal, glass, it doesn't matter. So now you look at the weight. Well, the weight is going to be the gamma times whatever volume the thing is. So you take the volume over, put over here, and that's going to give you your weight. I have the 62.4, but I don't even need to put that in. It's just a kind of a setup. Now, the volume I have is the area times the height. So if I want to look at it, it's the area. Well, I said area, but here's your area times the height. Now, you do this a lot in mechanics and materials. You do this a lot in a lot of structures in which you slice an object, but you don't really, you're not physically, like you take a beam and you slice it and you look at the reaction forces, but you're not really slicing it. You're in your mind slicing it, putting a moment, a shear on it to keep it there. But this is a visual exercise. It's not a physical. So in this, we're going to do the same thing. I'm going to take the glass over, and I'm going to strip the glass away from the water. And now this is just a column of water sitting there. And what is the pressure on the bottom? And here, instead of drawing it with the, I'm going to look straight down it. So it looks like this. I'm looking straight down it, but it has a circular cross section. If you're sitting here looking at it, you're going to see a circular cross section. But I'm just drawing it that way because I can put the vectors on there better. And it turns out there's a certain amount of pressure equally distributed on the bottom of that object, the object being the water, in order to keep the thing from flowing out on the ground. Because, you know, if you take the jacket, whether it's metal or glass, you take it away, you have to put the equivalent load back on it to keep it stable, just like you did in a beam. You took the beam, say it was simply supported, you did something like that, and you put this load on there so that it remained fixed. So that's kind of the mentality we're doing here. Kind of like free body diagrams, but maybe a little bit different because it's a fluid, I don't know. So it turns out this is nothing more. The pressure on the bottom is nothing more than a force times the area, which that's the same area as back here, so I could actually list that. And so what is that? If you look at this, you take this, and then you take that, and you look at it for a minute, you're like, hey, wait a minute. The weight is this thing. This is the force you're having to put back, so you've got a weight here. So this is the weight. It's the same thing as the weight over the area. It's the same thing. or gamma HAC over AC. And it turns out that the pressure is H times gamma. So if you're at water, you're in water, say, I mean, it doesn't have to be water, and you decide to swim down in the water, you're experiencing an increase in pressure by swimming down this H by a value of gamma times H. So if gamma isn't very large, you don't experience much by moving every foot. But in this case, I guess 62.4 is reasonably large. So the question is, what's the pressure at, say, 100 foot of depth? If you're looking at 100 foot of depth of water, 62.4 pounds per cubic, sorry, my hand went weird, times 100 feet is 624, and move a digit over once, so it's 600 pounds per foot squared. Now, if you wanted to, some people don't like that, they like that, and so I don't know here. Hang on a second. This I can calculate with my calculator, I believe. I can calculate it, I don't know that. Okay, so 43 1/3 PSI increased by dropping 100 feet. So I don't know how many atmospheres that is, but it's definitely more than one. So this kind of shows that once you dive in the water and you start going down, you start increasing your pressure. Now, there are these divers, what are they called? Not free range divers. What are they called? Free something divers.
Free divers.
Is it just free divers?
Free diving.
Okay.
Referring to no tank.
No tank.
Regulator.
So you're jumping in there, you have a regulator, you have a tank, and your lungs, imagine it's just essentially, you inhale, it's like a balloon. And then what happens is you put the balloon down in water. Here, let me make it. So here you are on the top of the water, and you shove the balloon down. The deeper you get, the smaller the balloon gets, because the compression of the outside is squishing the air down. You could figure that out if you wanted to, but free driving, you can't go very far. There have been records, and what they do, I think they get on, there's a rope and they hang on to it and it takes you all the way down, and then it has to bring you right back up. So apparently this is a very difficult thing on your physical body. But then regulators are another thing that kind of save you, and that is, okay, I'm not a good artist, but say, here's a person, well, they wouldn't be wearing a hat, but anyway, okay, so here you are, and here's your mouth. Obviously you can see why I'm not an artist. But here's his mouth and here's his lungs, and he's got this tank on his back. This is an awful drawing. But he's got this thing around his mouth that goes around and comes back to this funny looking object and goes into this tank. Sometimes these are around 3,000 PSI, so it's really pressurized quite a bit. It's got a lot of pressure in it. So the last thing you want to do is just open that up and have 3,000 pounds go right to your lungs. It would just pop your body, blow you up. So that's what this regulator is supposed to do. So let's say at the surface, it's just there. As you get down, instead of your lungs being that tiny at this depth, it figures out, so here's your regulator. It's obviously touching the water out here, and it obviously has, here's your tank at 3,000, this is a pretty bad drawing, but 3,000 PSI. What you want to do, you want to regulate it, the pressure coming into the person's mouth, to be the same as the pressure that it senses in the water. So in essence, what it's going to do is it's going to fill your lungs back up to about the same it was up there. So as you start swimming down, Now, you still don't need to turn around and come back up fast if you stayed in there too long, because, you know, if you were 100 feet, then inside pressure would be 32.3 PSI gauge in addition to 14.7 if that was the sea level. And so you'd have that pressure plus this, so your absolute pressure in your lungs at that point would be 43.3 gauge pressure plus 14.7 atmospheric pressure. That would give you the actual absolute value in your lungs. Now, I don't know what that is. 7 and that. Oh, that's pretty convenient. 3 and 4 sevens. That's 8. That's kind of interesting.
Let's say 58.
Is it 58? Oh, yeah.
58, yeah.
So that would tell you what your pressure is, absolute. So you don't really want to go from 58 to 14 real quick. You want to come up. What do they call it? The bends or something, where your nitrogen gets weird or something?
That, and then you shoot oxygen into your blood vessels.
Oh, okay.
Like you shoot literal oxygen balls through your blood.
Oh, that's maybe where the bends come from. Then is from that. It has something to do with that. I know there's bubbles, but I also know there was something to do with nitrogen, but I can't remember.
Nitrogen poisoning is referred to like fuzzy hangover.
Oh, is
in
that?
fact, like you start acting like you're hungover.
Oh, okay.
And you can catch that at any depth.
Oh, okay.
But if you change your pressure minutely, my uncle used to be a scuba diver.
Oh, really?
So like, we've talked about this.
Oh, okay. Did he have a thing? Isn't there a rule? You got to go with a buddy or something? Isn't there something? Or is there?
Since he was an instructor, he went on and got his dive team rescue certification. So he could dive by himself if he had spotters above ground.
Oh,
like
okay.
Right around boats.
Oh, okay.
But yeah, you're not supposed to go without a buddy.
It's such a, to me, you're putting a bomb on your back. I mean, literal bomb.
Or life support.
Yeah, or life support. I mean, 3,000 PSI is a lot.
Either bomb or life support. Depends on if you checked it to make sure it didn't become a bomb.
Right. But the only other thing I've seen, and I don't know if you've seen this, and this is off topic, but there's a new set of BB guns that, and this was probably 10, 12, maybe even longer, Marauder and some of those, that they use a pump to pump up the tube in the BB gun to like 3,000 PSI.
And then you can shoot it like 10 times.
Yeah, you can shoot it, and it's like, so it's almost like this. So what's interesting is there are people that buy the same pumps for these things and pump their BB guns up with. But the pumps are not cheap. So your BB gun is like $500, your pump is like thousands of dollars. And it's like, wow.
Yeah, but if you're a felon, you can't own a firearm.
Yeah.
That's a whole nother.
Yeah, there you go. So we won't go there.
Yeah. Whole can of worms right there.
Exactly. And we're videoing the lecture, so we don't want to open worms up. No, we can put worms on the board, but. So, we know this. We know that that's the case. How do we use it in engineering, or use or analyze? And there's 2 or 3 ways you do it. First thing is a manometer. That's the first. Okay, so, and this is used a lot. You know, you can go out to Walmart or wherever, and you can get a boron tube pressure gauge. Usually it's just funny looking pressure gauge, has the measurements and has the thing. But in the back, I'll leave that, I don't know why, but on the back of it, what it is, it's like a balloon. And so, I'm not a good drawer, so this could be a varying thickness, the metal, are a little bit different substance or geometry, so that it's attached, it has a little attached to the gear, and usually a little pinion sits on it. And then there's some sort of pressure or spring that pushes that against the pinion. So when it gets higher pressure in there, it pulls back and it rotates that pinion. And so this is commonly called bourdon. I don't even know how to say it, so I'll just start there. And it's in the book. But then you can go get, nowadays, you can go get a Raspberry Pi, and of course you may have to wait for it to come to stock. And for about $8, you can get this pressure gauge that you connect to your Raspberry Pi, and it can read the pressure straight off of it. These little gauges, they're smaller than your pinky nail, sometimes even smaller than that. And usually you can put them in different places. I don't know if you put them in chemicals or something, it'd probably ruin them. But for air pressure, it works okay. And there's all sorts of different pressure gauges. There's capacitance, where you just take big metal thing, and then you put the higher pressure over here. It bends it down, and you take the measure of the capacitance of these two. As it got closer, it would increase the pressure. So there's different types of pressure gauges. But the one that's the old standby is the manometer one, because most all of these, even this one and these, are going to have to be scaled or calibrated. They're going to have to be calibrated. Most of the time, this is done in the factory. It's, as long as you have good quality control, all of them are coming out and they're all okay. If you have bad quality control, you've got to do something about it. The silicon ones probably operate off of that and measure the capacitance, but I'm not sure how they do it. But then the Raspberry Pi, you can get pressure, temperature, and humidity, and chemical, all these different things, $9, $10. And that's about all you have to pay for them. I don't know how accurate they are. But the old standby is, here's a pipe coming at you. And here's another pipe coming at you. And maybe, so the flow is going like this way and this one, and maybe it's coming this way, and it goes down into some loops, maybe into the power supply, maybe into, maybe it's out there, energy, I don't know. But you want to know the pressure difference between these two pipes, pipe A and pipe B. And say water is going in between. So you can measure it by doing this. And one of the things that you got to be careful of is if you don't put the substance to measure the pressure in there. Let's say this is the high pressure, and let's say this is the low pressure. And you don't do anything, what it's going to do is just going to make fluid go down this pipe and into the other pipe, and it's just going to pull down the pipe. So what you do is you put like mercury in there, something that's pretty heavy, and it stops the flow. But also what it does is it shifts, and so what you get is a height difference right now. So the question is, how do you use this and this physical geometry arrangement, which is a manometer, to figure out what the PA is related to PB? And this is the way I like to think of it is, and the way I first do it is identify the location, say 1 and 2. Reason these are identified is, say this is mercury, so specific gravity is around 13.6. So in that, you're looking at it and you're saying, okay, I know this is heavier than the water, so now I'm going to find the pressure relayed from this to this surface, and then from here to here, and then from here to here. So if you start at pressure A, so I don't know what pressure A is, but I know it's a pressure. And then let's say this is, I'm just making stuff up. So this is 2 feet, this is 2 feet, and say these are at the same level. So if I basically swim down, so as I go out here, I go down, I'm going to a higher pressure. So as I swim down, I go to a higher pressure. I start here, start at A, I go to a higher pressure. I actually go 4 feet, or the H, and I'm going through water. And I stop it. I say, I'm going to stop right here. So if I stop right here, that's going to be equal to the pressure at location 1. So again, the way I do this, I start at a location. I go, if I'm going down, it's a positive. If I'm coming up, it's a negative. Because as I swim down into the water deeper, I'm going that depth through water. When I get to that depth, I'm at P1. Does that kind of make sense? So, let me do it this way. Start at 8. That way I can ride under this and won't mess up. So the next thing I do is I start at 1. So here I'm starting at 1. Let me make sure this is getting picked up on the... Yeah, that's just right there. So I start at 1. Now I'm swimming up. So what I do is I swim down through here. I swim up to this location. So as it turns out, if I go down 2 feet, I'm back up 2 feet. I'm at the same pressure here that I was here. So then I swim up 2 more feet. But this time I'm swimming through mercury. And I arrive at P2. And then I start at 2. And I swim up another 2 feet. And this time I'm swimming back through water. So this is water right here. Swimming up 2 feet. And I end at the pressure at location B. So I have transposed myself from A all the way to B. And the way, and what you could do at this point, there was a purple marker here a minute ago. Where are we? Oh, here it is. So now if I do this, I say, okay, I'm going to move this on this side of the equation. When I do that, I'll get this equals 0. I'll do the same here. And then I add all of these up. If I add them up, then the starting spot, this, cancel. The starting spot, and this cancel. So then I've got the entire journey without stopping. In other words, I start at A, I go down 4 foot through water. I don't technically stop, but then I turn around and go up 2 foot through mercury and up 2 foot through water, and I arrive at B. So you can do it intermediate steps, or you can do, but you have to identify when you change the fluid. You change from water to mercury right here, change from mercury to back to water right here. So if you wanted to do a complete journey, you could say, I start at A. I go down 4 foot through water. Then I come up 2 foot through mercury. Oop. Then I come up another 2 foot through water, and I arrive at B. Now, if you want to do it the reverse way, you want to start at B, you find out you end up with the same equation. PB, I start here, I go down 2 foot through water. I go down 2 foot through mercury. back up 4 foot through water, and I arrive at PA. Now, you'll notice each and every one of these has an opposite sign, and that's PB is on this side now, PA is over here. So if I took all this, moved it to the far side, every term would become switch signs. It would be with PB, but it would switch signs. So these are exactly the same equation. It's just my journey went different. I started from B, ended up at A. The other ones I started at A, ended up at B. So it's exactly the same equation. It's a complete journey. The way you can label it is, I start somewhere, I go plus or minus, and this would be down would be plus, up would be minus. I go down a distance h, distance I go, and through what material I might be going through. I'll put a question mark. Yeah. And so that's all you have to do there, just 3 things to take care of. Whether you went up or down, how far you went, and what you went through. And that's it. That's all you can do. You just go to these, you can go through manometers like crazy. As long as you can swim from path A to path B through different substances or anything else, you just, as long as you keep track of how you put these together, that's all you need to do. So that's manometers in a nutshell. That's pretty much it. So let's see. After manometers, let's see. There's some interesting equations that I can do, which I'll do 1 or 2 of those in a second. But does that kind of make sense? And what I'll do is related to free body diagrams in a second. I'll just do one of those tank problems from ages ago, but I'd have to remember, let's see, I'm sure. Okay, so we'll do one more of those things related to using that's kind of strange. And let me get a drink and I'll go back to it. So does all that make sense going up and down through it's actually pretty simple. I have seen, there was a book years ago I had where the guy had, I don't know why he did this. I think he did it just out of confusion. So he had a pipe, and then he had another pipe over here. And the pipes went in to this little cage-like thing. And this box was like this, and it was meant to confuse people. And what he had was little things like this, in which it was like a maze he had built, like something you'd get at Cracker Barrel or something. And so it was kind of funny. Some of them had air bubbles up here. It was meant to confuse people. And then some of them had, specific gravity equal to 5, and say down here, SG would be 13, and then this would be, so the key is if you started, you have to be able to swim through it to get to the other part of the maze. And so you went through all that, But all these others you didn't go through. And so as you went down it, you figured out where you crossed the liquids, and maybe this was some other liquid here, and maybe it was up to there. And the rest of it, this didn't matter, that didn't matter, none of this mattered, because you didn't go swimming through it. And so only where you went swimming through it. I thought it was an interesting problem. You could almost get something like from Cracker Barrel and draw two pipes on it and say, find the pressure differences between it. It would be kind of silly, but it's a combination of being a third grader and an engineering major. But I thought that was interesting. He put it in there. He probably had kids about that time, and he was probably going to restaurants and seeing those, and that's probably why he put that in there. Okay, so one other thing, there are many, but this is a side issue, which actually isn't a side issue, but something that might show up one day. And this is, I don't know if this is a problem in that book, but let's say you had a spherical object in which you had vented to the atmosphere, and it was connected on a like this, and there were some bolts through it, and there was a tension up here holding this thing up, and you want to know the total force on the bolts. And say, in the book he had it like that, but you could do it, you could even change it if you want to, but for the time being, we'll do it like that. So it's a sphere, and the volume of a sphere is equal to 4/3 pi r to the third. And maybe he did it that way because you just had one equation to deal with. And so this goal was, you fill it with water, say that R, I'll just make it up. R is equal to 10 feet. You fill this with water. Say it has the sphere itself is made out of weightless metal or something. I mean, just so you didn't have to use that in calculation. And you want to know what the total force on the bolt is. Well, the first thing you could do is it's filled to the top. You could go in here and start swimming. And as you swim down, inside the thing, pressure is equal to gamma H. So as you swim down, let's say you swim down to the point where you're right in the center of the thing. So I'll basically draw the object like so, and that's supposed to be a circle. Doesn't look like one. Let me see if I can do a better job. So that's a circle. But by the time I got to that circle, the pressure is equal to gamma times R, where R was the depth that I swam down to get there. So that's 62.4 times 10 feet, or 624 feet, pounds per foot squared. So in essence, if you were going to draw a free body diagram, what you would do is you would put a uniform pressure all across the top of this thing. And that pressure would be, you know, that 624. Yeah, that ended up pretty good. Likewise, you've got a bunch of water in here, which the weight of the water is equal to gamma of the volume of the half of a sphere. So that would be 62.4 times 4/3 times pi which that's a little bit, if you think about it. The pi divided by the 3 gives you a little slightly greater than 1 times 4, so it's like 4 point something right there. And then it's 10 to the third, but it's not the whole thing, it's only half of it. And that's the volume of the other half. Now the thing is, there is a weight of water up here, and this weight is sort of X'd out because in our mind, we're slicing it right here, and we're separating the top from the bottom, and we're only looking at the bottom. When you look at the bottom, you see a pressure across the top of 624. You see a weight, and then you see the total force of the bolt. So force, bolt, total. Now when you get done, if you have 8 bolts, you divide whatever that number is by 8, and that'll tell you the force per bolt. You're probably searching for how many bolts you need. That's probably what you're doing. Since it's a fluid statics problem, all you're doing is sum of the force in the y equals 0, and I guess I'll make that to be positive. And so I've got the force of the bolt totals, all the bolts, minus 624 pounds per foot squared times the circular area that it's pushing on, pi n squared. In addition, you get the gamma, and it's going down, and this going down. So this is going up, that's going down here, and this is going down. 62.4 this time, times, well, I wrote it all out here. So all I'm doing is copying this and putting it in there. So it's 4/3 pi n to the third over 2. And actually this should be alongside that, but so what you get, force bolt total for a 10 foot diameter sphere.
You mean radius?
Radius, yes, radius. That's, oh yeah, that's a 20 foot diameter. So that's a big, big thing. So let's see. Let's see if I can do this. 624 times 3.14159 times 100. Oh gosh, okay. 196/35. I'm just dropping the decimal spots at this point. And then I gotta add this one. Oh gosh. Okay, so. Okay, 62.4 times 4 times 130,609. Wow, that's a lot. So I got 326,725 pounds. You would probably want to divide that amongst many bolts. I don't know how many bolts, but you got, gosh, you got 20 foot. Wow. You got a 20 foot diameter, you could divide it amongst, maybe 120 bolts. So if you did amongst 120 bolts, you'd get about 2,722 pounds per bolt. I don't know how many bolts you want to put on there to hold that thing, but 20 foot is a lot. 20 foot in diameter is a lot.
Well, that would only be 1 bolt per foot.
Yeah, that's true.
Right.
Well, actually, yeah, because the perimeter would be what, 2 pi r? Isn't that right?
Yeah.
So it's 10. So actually, yeah, that's not even that. That's okay. So 10 times 2 times 3.14159. The perimeter is 62 feet. A little over 62 feet.
Yeah.
Yeah. So every 2 foot. Is that right? Or every half foot? No, every 6 inches. Yeah, a boat could handle that, 2,700, or, yeah, 2,700 pounds.
A big bolt could.
Yeah,
Good luck with a half-inch bolt though.
yeah. I wouldn't want to risk it with that, but. So this is a case in which, now here's what it confuses people sometimes that you don't take the upper part of this. And what actually happens with that upper part is if you look at it, let's take the steel jacket away. We're looking at the steel jacket. That's a pretty good cylinder, actually. So actually what you get is a pressure down here. I don't know if I actually, yes I did. It's 624 pounds per square foot. And it's the same over here too. So there is a part of this that's pushing in all directions. But what happens is when you get to this very top, it kind of goes to zero. And what's happening is all these pressures are perpendicular to a tangent of the surface of the circle at that point. So what's happening is there's an element of this water that is pushing upwards on this as well as out to the side. So when you get, when you get right here, you don't get that. But when you get right here, say just as a case in point, you get a value that's pushing up as well as to the right a little bit. And of course, as you get up here, so this upward push actually offsets. And you can go through the math, but it's kind of a fruitless exercise to go through the math to sum up all those to find out that actually the sum of those is the difference between the cylinder placed over it. This is a weird thing. So if you place a cylinder here, and then you put your sphere in it, so it comes up, touches right here. This void right here is what offsets that upward movement, upward. And it'll make sense later when we start doing gates and stuff. Curve gates, it's pretty, there's a case where it kind of becomes pretty apparent what's going on. But without saying too much, the best thing to do is slice it at the bolts. And then you've got a uniform pressure on the top, a weight, but you also have the weight of the metal, which is why I said it was a weightless metal. And if you can find a weightless metal, you probably can make billions. So, if you find a weightless metal, then you can build a vehicle like they have on the Star Wars. Notice all those vehicles that float. You park them and they get out of them and they're just sitting there. There's no tires. So if you can find weightless metal, it's got to be out there because Star Wars has it. So we're pretty much at the end, I guess. And that's about, I can see where you can't go much more than that. 3 hours lecturing straight, it wears you out. So I'm going to go rest my feet somewhere. We will start, so on Friday, we'll do gates, and then we'll start getting set up to work a bunch of problems all next week on chapter 1 and in chapter 2. Okay, put the microphone over in here, and it'll probably cut off. Did it cut off? Oh, wait, what do you do? Oh, wait, it cuts off automatically, huh? No, it doesn't. It keeps going. That is wild. Is that the microphone? Did I have the right microphone? I don't know that I did. It may have been the other microphone. three microphones in